Hi guys, I'd like to do a quick recap on electromagnetism for G485. A number of people have said that because we did it quite a while ago that was a bit tricky to remember. So, electromagnetism, we're going to cover magnetic fields, electric fields and charged particles moving through both of those. The forces that conductors experience, what happens when you have changing flux linkage in a coil, alternators and motors. So those are some of the things we're going to be covering. Okay, so let's get started with the first bit, which is take a permanent magnet and the magnetic field patterns that you get. So I'm sure you're all familiar with a permanent bar magnet, north at one end, south at the other, and then you have your field lines going around something a little like this. Okay, some going a bit further out. And the direction convention for magnetic fields is north to south. So draw your arrows on there like that. Okay, so that's a permanent magnet. And what those lines represent is the magnetic field. They tell you the direction, but they also tell you the strength. If you had a stronger field, then you'd have more lines per unit area. So a stronger field, you might have more lines like this. Okay. So you get the idea. More lines, stronger field. And then we have some terms to measure our magnetic field as well. So we've got flux density with unit of Tesla, and that's actually defined from an equation that we'll get to in a moment. So that is the force experienced by a conductor per unit length, per unit current that it's carrying perpendicular to the magnetic field. And then we have flux, and that is equal to B times A times the area that you're actually considering. That is unit Weber, and then you have M phi, that's flux linkage. This is where you have a coil, and this is the flux through that coil multiplied by the number of turns. And because you're just multiplying the flux by a number of turns, there's no unit associated with the number of turns, so they both have the same unit. A couple more magnetic field patterns that you need to know about. You can have, whenever a current is flowing through a conductor, that produces a magnetic field around itself. So, and in these cases I'm looking at when you have a direct current. If we have, let's say we've got a wire coming out of the board, so a dot indicating that it's coming out of the board, okay? Now in that case, that has a magnetic field around it, and what you need to do to find out the direction is use the right-hand grip rule. So if you make a grip with your right hand, then your thumb is pointing up and your fingers are curling around. And what they indicate is that this is the direction of the current, conventional current, and your fingers indicate the direction of the magnetic field. The magnetic field pattern is circular, so in this case it's anti-clockwise. Circular around here, and it's concentric circles which get a larger spacing as you go away. And that makes sense because the magnetic field is obviously going to be stronger near the wire. So it's anti-clockwise, so you need to have both of those in there. If you had current going into the board, so you use a cross for that, then you'd have the same pattern especially if it's the same size current, then it would have similar spacing, or the same spacing as this one here. Okay. And this time, right-hand grip rule is going into the board, so this time the arrows are in the opposite direction, they're clockwise. That's for straight conductors carrying a direct current. If you have an alternating current, then what you would have happen is firstly the direction of the magnetic field will change, obviously, because current changes direction, so then your right hand grip rule is going to give you a magnetic field in the opposite direction. But also it's going to be changing in magnitude, because direct current, alternating current doesn't go from plus 13 amps to minus 13 amps straight away. It's a sinusoidal change. So the magnetic field will collapse in on itself and then expand back out, and then collapse in and expand out. So that's what would happen. I doubt that you would get questions specifically about that. If you have two conductors like this near to each other, then their magnetic field will interfere with each other, and so you can get your conductors to either repel each other or attract each other. And we'll see how that may work out once we understand how magnetic force and current is related. Now let's take our one conductor here. That's a straight conductor. So we've taken a cross section. But what if you take your conductor and then coil it up into a solenoid? Well, what you would find happen actually is that all the magnetic field along the length of the conductor will combine and give you a field pattern similar to our permanent magnet over there. Okay, shouldn't have got that. Okay, so you may have set up like this. This is a basic solenoid, and how it will amalgamate is if you were to use the right hand grip rule at any point. So let's say as it's going up here, let's take this one again. It's going up on this loop here. So as it's going up, right hand grip rule tells me that inside the coil it's forcing the magnetic field is going this direction. Well, that's going to be the same all the way along at these points as the current is going up on this side, so on the outside of the board. So it's forcing the current all the way along the magnetic field all the way along there. On the other side, where it's going down, well, if you imagine you're behind the coil, then the inside, the magnetic field is going in the same direction. So what we get is these field lines going all the way along here like this, and then when they exit here, they haven't got that effect of the coil and the circular pattern of the field lines, so then they start to expand out and even go all the way around back to here. And that would be true at whichever point on the coil you looked at. Okay, so you'd get something like a permanent magnet. And this setup is called an electromagnet. And you notice that the field line is coming out here. Now, there is an easier way to find out which side is north and which side is south than using the right hand grip rule on all the loops. If you were to look at that side of the coil end on, so you would have something going like this, okay? The current is going up like this and curling around like that, okay? Now, one end has to be north and one end has to be south. It turns out actually that if you were to draw a north in here, draw an N, and put arrows on the end of the letter N, then they match up. That anti-clockwise rotation matches up with the anti-clockwise rotation of the coil. And if you look at this end, so then here we have the coil rotating around and then going down like this. So at this end, if you were to draw an S in there, and put arrows on the end again, then they match up there as well. So north, the current will be going anti-clockwise, and south, it will be going clockwise. So that's a useful tip to remember for finding out the magnetic field direction for a solenoid. Okay, so that's our magnetic field patterns. So let's have a look at some situations where magnetic fields and charged particles interact. When charged particles move through a magnetic field, they experience a force because there's a relationship between electricity and magnetism. Hence, we talk about electromagnetism. Let's say we have a positive charge here and it's moving to the right here with velocity v. When it enters a magnetic field, it will experience a force. Let's define our field. It's going to be a uniform field. Okay, the size of the field, the size of the strength is BQV. So it's the flux density multiplied by the charge multiplied by the velocity. That tells us the size of the force that it experiences. In order to know the direction, we need to use Fleming's left-hand rule. The force is going to be given by the direction that the thumb's pointing. The flux density, that's the direction of my finger, and the direction of the current, which will be, we'll have to work out based on the velocity and charge of the particle. That's my second finger. They're all perpendicular to each other. You have to hold them perpendicular to each other at all times when using Fleming's left-hand rule, and move your arm and your wrist in order to line them up. So you can't start moving your finger, your second finger, so that it's more parallel with your first finger. They all need to be perpendicular because it's the perpendicular components that count for magnetic forces. In this case, we have a positive charge. Now, a positive charge will move in the same direction that conventional current flows. So our current direction is to the right. Our field direction is into the board. That's what the crosses indicate. So it's into the board, and that means it'll experience a force upwards. So FB for the magnetic force. Now, that's going to cause the velocity vector to change direction. It's perpendicular to the velocity vector, so it's not to change the magnitude. So if there's nothing decelerating that charged particle, then it will have exactly the same velocity vector at the new angle that it's at. So let's just put that there. Charged particle is here, it's got velocity vector v. So I know I didn't draw it very well, but hey, just imagine. And now let's consider the charged particle there. Well, we use Fleming's left-hand rule again, and because the velocity vector is unchanged, but it has changed direction, it's unchanged in size, we experience the same magnitude of force, but still perpendicular to the velocity vector. That's going to cause your charged particle to move in a circular path. So the charged particle will undergo circular motion as long as it's in the magnetic field. If my field ended here, then once it exits, so going in that direction, it will continue to move at velocity v without changing direction. If you reverse the field direction, then what we need to do is point my finger outwards, and the force will be down, so it undergoes circular motion going downwards instead of upwards in that case. So that's a charged particle moving through a magnetic field just by itself. It's not in a conductor. What if it is in a conductor? Let's get rid of this now. I've got a conductor. Let's have a different field direction this time. Okay, that's our field there. That's right, there. In this case, the conductor would experience force only the length of the conductor that is in the field, and the force would be F equals BIL sine theta. So it's the flux density multiplied by the current flowing through it and the length of the conductor which is actually in your field. I said earlier that I would tell you the equation that defines flux density. Well, that's it. So that's where you get the definition from for flux density, rather. Okay, now in this setup, you can see that the field is coming out of the board, current is to the right, so they're perpendicular to each other. And the theta is the angle between the current and the flux lines. So in this case, if theta is 90, then sine theta is 1. So the force would just be B times I times L. If you have an angle which is less than 90, then you'll need to just appreciate you've got the sine theta there. You also need to make sure that your how you look at theta is the right way around, because you need to have the components which are perpendicular to each other. So let's try and draw a diagram to show what I mean there. That's our current, and here is B. That's our field. That's I. So in this case, there's a component which is parallel with B, and there's a component which is perpendicular. It's the perpendicular component that we're interested in. So theta would be here. So then sine theta will give us the component which is perpendicular to the field lines, and that's the component that contributes towards the force. So that's the angle we would need to use there. All right? Just watch out for that, because sometimes that can lead to mistakes. Okay, now that's just a straight conductor through our field. Let's take a coil, a square coil. Now, the thing about our coil, it can rotate around this axis here. Okay, it can rotate around there, and over here it has slip rings. Now, those are important because what that will allow the coil to do is rotate independently of the battery contacts. This is the battery providing a direct current, so that if the coil rotates over to here, so this contact of the coil is now on this side, well, it's slipped in the slip ring so that the current will continue to flow in this direction. So it will continue to flow in this direction around the coil. So that's an important thing. And now let's put this coil into a magnetic field, like this. So you might have what's called a yoke of magnets. I guess, something like this. You've got a magnet over here. One side is north, the other side is south, so then you get a uniform-ish magnetic field going north to south, like this. So that's our magnetic field. Well, we now have a current-carrying conductor in a magnetic field, so it's going to experience a force. Fleming's left-hand rule. The current is going into the plane. Now, this is a 2D representation of a 3D reality. So the current is into the board. The field is over to the right, so I need to rotate my hand around. And this side is going to experience a force downwards. Okay, what about this side? Well, you can appreciate the fact that the field is in the same direction, but the current is in the opposite direction, so it's out of the board. This one experiences a force upwards. So what we've done is we've set up a couple on the coil, and that will produce a torque and cause it to rotate. And when it's up here, it's not going to experience a force because the slip ring is going to stop allowing current to flow. But the momentum that the coil has gained will carry it through that position, and then once the current starts flowing again, we'll get that downward and upward force couple, causing it to still experience a torque. So that's the basic principle of how an electric motor works. This is called the motor effect. So that's our coil in a magnetic field. Right, electric fields. We'll start off with the convention for your electric field. Firstly, the lines. We're going to use lines just like we did with the magnetic field to represent the field. The lines leave and enter surfaces at 90 degrees. Number of lines tells you about the strength. And number 3, direction. That a positive charge would move. So those are your 3 things there. So let's take a uniform field. Parallel plates come up a lot in exams. I wouldn't be surprised if you got one. So positive, negative. Field lines must leave and enter the surfaces at 90 degrees. Mine aren't quite touching, but they should do. Okay, they're leaving and entering the surfaces at 90 degrees, and they have direction. If I put a positive charge here, it's going to be repelled by the positive plate, attracted towards the negative, so arrow is going down. If I reduce the strength of the magnetic field, the electric field, then I need to have fewer lines per unit area there. So just rub out some of these. Yeah. So that's a weaker electric field now. That's a set of parallel plates. You can have radial fields as well. So you might have, let's have a negative charge there, negatively charged sphere. They leave the surface 90 degrees, and leave or enter. Okay, so here you have to take a tangent to the surface where you're considering it, leaving or entering the surface. This is a negatively charged sphere, so it's going to be a charged particle, positive particle here, it's going to be attracted towards it. So those fields going in there. You're going to have to be able to deal with cases where you have a negative charge here and another negative charge here. What happens to the field between? Or if you put a positive charge here, what happens to the field between? In those cases, I'm not going to go into detail about that, just look up in your notes. But in those cases, don't forget to draw either side of the charged particle as well. So let's say this is your diagram zoomed out. Then draw your field lines in all that area around the charged particles, not just in the middle of the two. Okay? Alright, so electric field patterns, electric field strength. Electric field strength is defined as the force experienced per unit charge. It has units of newtons per coulomb. Okay. And for parallel plates, the electric field strength is voltage per unit distance. Okay, so if you know the separation of your parallel plates and you know the potential difference between them, then you can work out the electric field strength there. So if you had a charged particle in your between your parallel plates, then you you can work out, and you know the potential difference of the distance, you can work out the electric field strength, then you can work out the force that the charged particle would experience. Let's say, classic example, these are vertical, you're balancing your charged particle here with the electric field strength at a certain value, then you can work out what force you are exerting on that charged particle, and if it's being held in equilibrium, then you know that force is equal to the weight, because those are the only two forces acting on it, likely. Okay, so Fe would equal the weight in that case. So you could either find out the weight or the mass, depending on what you were asked for. Okay, so charged particles, electric fields. If you have a charged particle moving through a uniform field, then there's a subtle difference between what happens in this case and in the case of moving through a magnetic field. So, if our charged particle enters here, velocity v, it's going to experience a force, if it's positive, it's going to experience a force downwards. But unlike so it's going to go in a curved path, and here's our charge here, but unlike in the case of the particle moving through the magnetic field, the direction of that force was always changing with the change in velocity, whereas here it's not. The force here is still downwards, so it's still experiencing a force downwards here. So what you actually get here is something like projectile motion. A projectile is fired with an initial horizontal velocity, and it experiences a force vertically downwards at all times. It doesn't matter where the velocity vector is pointing, the force is always down. Same thing here. Okay, so you don't get circular motion in an electric field. It may not necessarily hit the plate before it exits, it depends on its velocity, its charge, and the electric field strength, but it will undergo something like projectile motion whilst it's in between those plates. Okay, what if then, so you can have charged particles moving through an electric field, you can have them also moving through a magnetic field. What if they move through both at the same time? Okay, let's have a particle moving up here at velocity v. This is a positive charge. So let's set up a set of parallel plates here, and we've got a positive here and a negative here. That's going to experience a force to the right there because it's a positive charge. Well, we can actually introduce into this a magnetic field so that it experiences a force to the left. Well, let's see what direction we have to do that in. The velocity vector for a positive charge means the conventional current is upwards. The force we want is to the left, so my thumb needs to point to the left, so the field needs to be into the plane of the board. Okay, so we're going to have our B field into the plane of the board. Okay, so that will give us our FB to the left. If both of those forces are equal in magnitude, then the charged particle will be able to move through that region without deflecting. Now, you know that the magnetic force is actually dependent on its velocity, so this will give us a way of selecting specific velocity particles at a specific velocity. And hence today this setup is called a velocity selector. So what velocity would be undeflected? Well, Fe is E times Q, and Fb, that's electric, magnetic, is B times Q times V. So those two are equal, therefore EQ is BQV. Q is the same on both sides, so that cancels out. So the velocity that would remain undeflected would be E over, sorry, not V, but B. They all sound the same, these letters. Okay, so E over B. So you can select the velocity that you want for your particles to have as they exit your velocity selector by that equation. The electric field strength divided by the magnetic field strength. Okay, now why would you want to do this? Well, in a mass spectrometer you want to select particles that fulfill certain criteria to see how many of them there are in your sample. You could put them directly into a magnetic field, but then you have two variables. In fact, because this is providing the centripetal force, then you've got a number of variables. You've got the mass, how you're going to know what you're selecting is by placing your detector at a certain radius of the circle. So perhaps best if I actually draw the setup. You have your charged particles entering here, and then they undergo circular motion in your field, and this is where your detector is. Okay, so when you're detecting something there, you know you're detecting whatever you've specified your setup for. But yeah, going back to this, if you just use a magnetic field by itself, then your radius is what you're using to specify what you want, but that's equal to mv over bq. Well, b is a constant, but that means that you've got mv and q as variables. So that's not desirable. We want to eliminate some more variables. Here, what you can do is you can set your velocity, so you know what velocity the particles will have in this case. So then that becomes a constant. So you will have V over B, constant term, and now you can select your particles by a specific mass to charge ratio. So if your particles have larger mass, then they will have a larger radius and not reach your detector. If they have a larger charge, for example, then they'll have a smaller radius and therefore they won't reach your detector either. But so you can select for a certain mass to charge ratio. Okay, that's our velocity selector and mass spectrometer. So that's forces on moving particles, moving charged particles. What about the alternative? How about electromagnetic induction? It's actually causing charged particles to move by manipulating them with a magnetic field. Well, you can do that as well. So let's have a look at this.